Welcome to Strength of Materials 1. It's been much too long since we had last week, week 9, on composite structures. That is almost 3 weeks ago. Today we will have week 10, which is about beam buckling. So, beam buckling is a really important phenomenon. We will actually see that when we design structures, of course, stresses in beams due to bending are very important, as we have looked at the last weeks. It can often be the deciding factor when we decide how we dimension bars and beams, the dimensions, the thickness, and so forth. But often actually beam buckling also becomes a deciding factor, deciding how thin, how light we can make structures in reality. So having a fundamental understanding of beam buckling is very important when we want to design actual structures, both civil structures like bridges, stuff like that, but also mechanical structures. So, however, first we will just recapitulate what we did in last week, composite beams, and we will also look a little bit more on the stresses in composite beams. But first, a repetition. So, from last week. So, although it's 3 weeks ago, I hope you remember bits of it, what we did last time. So the fundamental question that we answered was how to compute the stiffness of beams when they are no longer homogeneous. So, for instance, when they are made of two different materials in different parts of the cross-section, we wanted to find out how do we compute the actual stiffness, so what we also know as the actual rigidity, but also, and perhaps more importantly, the bending stiffness of these composite cross-sections. So as we saw last time, there were 3 integrals which were really important when we wanted to compute these quantities, and H1, H2, and H3 were the fundamental integrals that we wanted to compute for a given cross-sections. So they were all integrals over the cross-sectional area. So the first question that we wanted to answer was, where is the elastic centroid C located? The elastic centroid of the cross-section. For certain cross-sections, it was obvious, for instance, that we had the elastic centroid in the middle if we had a symmetric cross-section, but very often our cross-section properties were not symmetrical, and we wanted to, as the first step in this process, compute the position of the elastic centroid. So the coordinate of the elastic centroid we call ZC, and we can see here from the equation that the first 2 integrals that we need to compute in order to find the location ZC was H2 and H1. So these had to be computed if we did not in advance or a priori know the location of the elastic centroid. So first step, computing H1, H2, and from those quantities we determine ZC. From there on, we could go on to computing the actual stiffness properties of the cross-section, that is the actual stiffness, the actual rigidity, which we call H1 star. So as it turns out, that property, the H1, turned out to be invariant to coordinate transformations. That means that even though we have to transform it to the coordinate system located in the elastic centroid, that did not make a difference to the value of H1. So meaning that the H1 we already computed up here is the same that we have here. So we already have H1 star, which is the actual stiffness of our composite. So no new integrals to be computed. As we can see here, with our new coordinate system and our known location of our centroid, our H2 star is actually defined to be 0. So no need to compute H2 star. We know it's 0. We can use it to check the value of our ZC, of course, and that is a possibility. So having computed ZC, we could insert it into this formula and check that the integral indeed has to vanish. So, but the final step is then to compute the integral H3 star, which we then can use as our bending stiffness for the composite cross-section. So this is very shortly the main components of the composite beams theory that we covered last time. So there was a second part to it, and that is in certain cases we can use simpler formulas to computing the bending stiffness and the actual rigidity, and that is if we know if we have something which is often seen in real life, reinforcement with very small fibers. So what do we mean by small fibers? It's of course difficult to make a precise definition of what a small fiber is, but well, you could maybe as a guideline say if you can see them, they're not really small enough, right? We need to have very small fibers dispersed uniformly in our matrix material. So our matrix material here, we can see as the gray part of our cross section, and then the reinforcements, which are stiff fibers, are the circular inclusions in our matrix material. So the point here is that if we do have such a uniformly distribution of very small fibers, then we do not need to make the complicated calculations that we did on the previous slide. We can make a much simpler approximation of the effective Young's modulus of our cross section, and then we can use that to compute our stiffness. So the effective Young's modulus of such a reinforcement case here will be what you can say a weighted average of the fiber Young's modulus and the matrix Young's modulus. And the weighting factors will just be the volume fraction. So this is the volume fraction of fibers. This is the volume fraction of the matrix material. And of course we have the connection that CF plus CM equals to 1. Volume fractions add up to 1. So that means that we can express everything in terms of CF here. So this is much simpler formula than having to compute all the integrals that we did on the previous slides. One last point when we talk about composite beams, so the last case here with the uniformly dispersed fibers, that is very important to have an assessment of the stresses in the fibers or the stresses in the material. So let's just have a slightly more detailed look at the stresses in the composite beams. So having said that we compute our effective Young's modulus with this very simple formula dictated by the volume fractions, then we know when we then actually find our moment, find our normal force, we can compute the stresses in our composite beam. But when we have done that, we actually have to remember that the stresses that we find with this formula are the average stresses in the composite material. It's not really the actual stresses in either the fiber or the matrix material. It's the average stresses seen as a sort of smeared out value of the effective Young's modulus. And this is of course dangerous because this tends to give a too low estimate of the actual stresses. As we can see here in these two sketches here, we can see that due to the high Young's modulus of the fibers, we actually get very large stresses in the fibers. And that's of course what can ultimately lead to failure in these fibers. If the stresses become too large, then we will have failure in the fiber material. So we need to have an assessment of what are the actual stresses in the fibers. And then we can use a very simple correction as shown here in the last formula, that when we have computed the average stresses from the top formula, then we can scale the values with the fiber Young's modulus and then divide by the effective Young's modulus and use this scaling factor to actually predict the actual stress in the fiber material, which is of course typically much, much higher than the average stress in the composite beam. So there will be another exercise today in the problem session dealing with the composite beams so that you can repeat some of the theory that you did 3 weeks ago. But then on to today's subject, beam buckling. So as I said, in reality, in real life constructions, beam buckling is a very important factor that we often have to take into account when we decide on the dimensions of structures. So here are just a number of examples from real life showing different buckling scenarios. While this may not look like what you think of buckling, but think of the thermal stresses coming from a thermal expansion when we have a temperature increase of a railway track. So this leads, of course, to actual forces in our railway tracks. And this in turn actually then, as you can see here, if the temperature increases too much and the stresses, the forces, actual forces become too large, we will actually see buckling of the railway tracks like this. So buckling will be an effect where we have actual stresses or actual forces that become too large, and then we will suddenly have what you can think of as a snap of our beam bending out to the side suddenly. So it will not like bending, where we have seen that our deformations increase gradually with our load, so that when we increase the load gradually, we will have a gradual increase in our deflection. Buckling is a completely different phenomenon. So we will have nothing happening for a large force, and then suddenly when the force becomes too large, then the structure will snap and bend to the side. So this is what we see in buckling here. It's the fibers of a reinforced concrete material that suddenly buckles here due to a large compression load. Of course, we can also think of useful effects of buckling. So when we have the action, the velocity or the speed of the athlete becomes large enough, and when he sticks this pole into the ground, then the force becomes large enough for the pole to actually buckle, and then you can use that to do these pole faults. This is a very large scale example of a catastrophic effect of buckling, when we actually have a whole vessel collapsing due to a buckling effect. So it's not easy to see from this picture that it looks more like just breaking in the middle, and it actually is breaking in the middle, but it's due to a local buckling effect of the shell structure in the bottom of the vessel, where the actual forces inside the shell structure becomes too large and then results in a funny buckling. Of course, when you have a plate buckling, it becomes much more complex than when we just have a beam buckling. But this is also a very important issue when you design shell structures. When do they actually buckle? And we have actually looked a lot on truss structures previously in this course, and one of the so-called motivations for truss structures to being so popular, and also why we have looked at them, is that they are very stiff, right? We see that truss structures are very efficient structures in terms of carrying loads. But again, if we have compressive forces in our bars, then the deciding effect on when these actually will fail will be buckling. So typically, when you design these truss structures, if you have bars, if you have truss members in tension, this is very nice. So if you have a bar that you pull, then of course you will have no problem with buckling. You can pull as much as you want. Of course, ultimately you will also have failure of a bar or a rod. If you pull it too much, then you will have what we call necking. You will have plasticity going on, and you will have a thinning of the cross section at one point, and it will ultimately break. But this happens at a very large force. But if you have truss structures in compression, then the thing happens that we talked about on the previous slide. Nothing really happens if the force is moderately high, but ultimately if your force becomes larger than some critical force, then your beam or rod will bend out to the side like this. So this will be the deciding factor. Of course, if you design your trusses in a very smart way, you will it will be beneficial to try to have as many of the truss structures being only in tension. But of course, in practice, this cannot always be accomplished. You will also have some truss members in compression, depending on the load, of course. So this is actually more or less what we will get to find out in this during this lecture. These are the basic formulas, so I'm just somehow giving a teaser here of what we will actually find during the lecture, these are the critical loads for different boundary conditions of beams. So this is actually the answer to many of the problems that we will, questions that we will pose in this lecture. So as we see here, what is you should pay attention to is that we compute here critical forces. So what we will find is that when the force that we put on the beam here, if it exceeds the critical force, then we will have buckling. And as we can see here, we can find explicit formulas for the critical force that we need to apply in order to have buckling of the beam. So what we can see here that the magnitude of the critical force depends on the boundary conditions. So we here have 4 different cases, and we can see the lowest critical forces. The lowest critical force, that means that the type of boundary condition that gives a structure that is mostly prone to buckle, is the clamped free beam that we will have as case 1 here. Now, if the force increases this factor, increases over this factor, which is this funny factor of pi squared over 4, and then a dimension factor depending on the bending stiffness and the length squared, if the force increases this increases to more than this value, then our beam will buckle. Our second case here, here we have a case of a simply supported beam, simple support in both ends, and then we see here that here we have to increase the force to 4 times the load that we had in the first case. So we need a 4 times larger load in order for this beam to buckle, due to the fact that we have constrained also the point where we have the force applied. Now, even higher critical load we obtain if we have the combination here in case 3. If we have a combination of a clamped support at the bottom and a simple support at the top, here we need to have a factor of 1.43 squared higher than the case 2 boundary conditions. And finally, the one that gives the highest critical force is case 4, where we have 2 clamped supports in both ends. Here we need 4 pi squared as the factor. So if we compare that, for instance, to case 1, we can see here that we need 16 times higher load for case 4 in order for that case to buckle than we had for the case 1. So how do we compute these numbers, and where did these funny pi squared factors come from? We will see that in the forthcoming slide. So just one final note about this slide. We can see here that we have this LE. So what does that mean? Well, we call that the effective length. So if we define, if we take as a benchmark the length of the second case here, we see here that if we can instead of having this factor in front, we can just define an effective length corresponding to each of the cases 1, 3, and 4 that will give the same buckling load as case 2. Well, that sounded a bit confusing, but we can see here that for case 1, it actually gives the same buckling load as if we had 2 times the length of case 2, and the same goes for case 3 and 4. It's not something that we use a lot. It's much more easy just to compute the critical load, but it's a quantity that we define as the effective length. We will go on to see how we actually can compute these critical loads for different boundary conditions. But before tackling the more difficult problem of an elastic beam, we will exemplify the calculations on a more simple structure, which is simply a completely rigid bar, which cannot deform. So we have a rigid bar here. So you ask, okay, so how can it buckle? When instead of having the elasticity of the beam, then instead we will have a moment spring attached in the bottom. So due to the moment spring, we can also experience buckling of this structure, so that when the force F becomes too large, then the beam will simply rotate and come out to an equilibrium position in a rotated position. So of course it's a completely different mechanism, you might say, than when an elastic beam buckles, but it shows some of the same calculations that we need to do with the more complex elastic case. So we will use this to illustrate the method that we will use to compute the critical load. So the figures here are not really self-explanatory, so I will just briefly show what we will do on a small drawing here in the end. Now, see here we have the case of the rigid bar. So this is our rigid bar here. Now rotated into an equilibrium position in a rotated position. So how do we actually find this position? Well, we assume that we have this rotated position, and then we actually try to compute the angle phi that will have to the angle phi that we have to have in order to this position to be in an equilibrium. So now we're back to statics. How do we find an equilibrium? Well, we could use sum of forces and sum of moments. So let's use the sum of moments around the rotating point. So the rotating point is O here. So what forces do we have in the system? Well, of course we have the force. The force gives a moment around the rotating point, our force F, but we also have a moment from the spring. So the characteristic thing about a moment spring is that it gives a moment which is equal to a spring constant that we will call the torsional spring constant, kT, multiplied by the angle phi. So this is the way we normally characterize a linear moment spring. So now our task is to find, okay, when is the system in equilibrium? So we will use moment equilibrium around the original point, or the origin. So the sum of moments around that point has to be equal to 0. So here we compute the moment of the force F. We can see it's negative. So it's force, and then we have to multiply it by the moment arm, and we have already indicated the moment arm by L sine of phi. Here. And then we have the moment in the moment spring. So these are the only two external moments on the system. So if this should be an equilibrium position, these two moments need to match. So the condition for equilibrium can be written as F times L times sinus phi equals kT phi, or for instance expressed as sine phi equals kT over FL times phi. Now let's examine the possible solutions to this equation. Well, the interesting thing is that there is always a trivial possibility. There's always what we call the trivial solution. And this is one of the quantities that we can carry on from this simple example onto the more complex elastic beam examples. We will always have the trivial solution. And the trivial solution is simply that the structure does not buckle, right? Phi equals to 0. If phi equals to 0, then we have moment equilibrium. The force doesn't give a moment around around point O, and consequently there is no moment in the spring. So that will always be a solution. Possibly a little bit surprising, because we do know, at least also from the elastic beam example, that at one point the beam will buckle. However, the straight equilibrium position is always a solution. The case is then it just becomes unstable if we also have another solution. But let's see, what about the other solution? We will, of course, call that maybe the non-trivial solution, but also refer that to buckling. This is an actual buckling case, right? So what is the condition for buckling? Well, we already have the condition up here. We have to solve this equation for phi. It's not an easy equation to solve because it's nonlinear. Of course, you can do it in Mabel or other mathematical software. But we can somehow indicate a graphical solution. Now let's draw the two parts of this condition, the sine phi. So this is phi along the x-axis. So the sine phi, we know what that looks like. Not a perfect drawing, but we know what the sine looks like. And then we can also draw the right-hand side of our equation. So here we can see it's a linear function. We have a factor in front, kt, divided by FL. So if a linear function is to be equal to the sine function that we were just drawing, so this is sine phi, well, we can actually identify two cases here. Our linear function could look like this. So this is kt divided by FL times phi. But this is the case where our kt divided by FL is larger than 1. So if the slope is larger than 1, we can see that the dashed line here never crosses the solid line, and the equation can never be fulfilled. However, if kt divided by FL has a value lower than 1, and that could be so this is then again kt divided by FL times phi in the case where kt divided by FL is less than 1. So we have a slope less than 1. Then we can see that we actually have a phi corresponding to our buckling case here. So in this case, we will have buckling. So we can actually write up the condition directly from this. So the condition for buckling is that kt divided by FL should be less than 1, or expressed in terms of the force, which then becomes the critical force, so the conclusion in this example is that if our force is less than the critical value that we just computed, then we will have the rod in its upright position, and that will be the solution to our problem. However, if our force exceeds the critical force computed, then the straight position, the upright position, is still a solution, but it's unstable. And that we could show, we will not do that. That requires a little bit more mathematics, but that will be an unstable solution. But we will have another solution as well. We will have the buckle solution, and that will be stable in this case. Now, this issue with stability of the solution is indicated in Figure C in this figure 7.1 from the book. So we can see here the indication of the stable equilibrium position, the upright position. For increasing F is a solution at this point, which is corresponding to the critical value of the force. The straight solution becomes unstable, indicated by a dashed line, but we get two stable solutions, of course the beam or the rod here can buckle to both sides. There's no preference here. And then we will have the two possibilities for buckle position. So already at this point, we can ask ourselves the fundamental question: why do they actually buckle? Why doesn't the beam or rod just stays in the upright position when it is in equilibrium position, even though it's unstable? Well, the true case, or the reality, is that we will always have some type of imperfection in our structure. It will never be perfectly straight. And in the case where we not have a perfectly straight rod, then the unstable solution will not be able to exist. So depending, of course, on the nature of the imperfection, that will also decide if the rod will buckle out to one side or the other side. That is, if we get this branch of the solution or that branch of the solution. That's all depending on the imperfection in our system. Okay, so this was a little bit a simple example that will lead us to the real case that we will like to address, which is the buckling of actual beams with elasticity, right? Not infinitely rigid bars. Okay, so, but here we will also take it a little stepwise. We will first consider a specific case of boundary conditions and look at that case first. So we will look at a beam with two simple boundary conditions. We already saw the answer to this question because it was part of the four cases that we saw earlier. So we know the answer. So now we just need to find out how do we actually find that answer to the problem in terms of the critical load. So what we do now here is, again, just like inspired by the previous simple example, we will draw our structure in a buckle shape here. And then we will actually do equilibrium conditions on the buckle shape. So if we look at the simple indication here of forces and moments on a beam in the buckle position, so we take out a short section or a short part of the beam close to the left boundary condition where we have the actual force. So now we draw the cross-sectional properties in our cut here. So of course we know from actual force equilibrium that our actual force will also have the magnitude F. And then we will have some moment. And we also indicate the deflection at that point that we will call W. So let's take a very simple moment equilibrium around the boundary condition here. So moment equilibrium around that point, well, we have two quantities providing a moment. We have the force with a moment arm W here, and that has to be balanced by the moment, the cross-section moment here, M, right? It's very simple. These are the only two quantities giving a moment around our boundary or our boundary point here. So the moment has to be equal to F times the deflection at that point. So we know some things about moments from our bending theory that we have covered the past weeks. So we know that the moment can be expressed by minus EI, the bending stiffness, multiplied by the second derivative of our deflection shape. So now we insert that into the equation above, and we get a homogeneous differential equation. So we can reorder that a bit, and we end up with a differential equation with a parameter lambda, which is defined as the force divided, or lambda squared, which is defined as the force divided by the bending stiffness. So this is the equation now that we have to solve using our boundary conditions. So here, restating the equation with the parameter lambda squared. So this is a well-known homogeneous differential equation. We can write up the solution in form of the sum of a cosine and a sine with two unknown coefficients, a and b, that we have to find using the boundary conditions. Well, we have here set ourselves on the boundary conditions of a simply supported beam. So we know that the deflection both at x equal to 0, which you have here, and at x equal to L equal to 0. Now, inserting those conditions into our solution form above, we find out that the constant A has to be equal to 0, and the second condition gives us that this condition has to hold. So, of course, there are two possibilities here. Either B could be equal to 0, and then we're back to the trivial solution. Then we're back to the straight beam position, which, as we saw for the previous example, is also a solution here. Well, but there is another solution, right? Because we can also have that sine of lambda equal to lambda times L equal to 0. So this will characterize the non-trivial buckle solution. So how do we solve that? Well, we can see here that the condition that sine of lambda L equal to 0 leads to this condition on lambda. It will be a multiple of the factor pi divided by L. And these values of lambda for different L are actually called eigenvalues because we have solved an eigenvalue problem. Typically, eigenvalue problems we find in vibrations, but here it's an eigenvalue problem referring to buckling. So here we find the lambda corresponding to our buckling loads. And when we solve for for W, we actually find the corresponding buckle shape of our system. We can see we have an arbitrary amplitude because we have not solved for B. We do not know the value of our constant B, so we can only define the shape and not the magnitude of the buckling. So, of course, we have a number of eigenvalues, lambda n, corresponding to any number of n, 1, 2, 3, 4, and so forth. But of course, the relevant one is the lowest one, corresponding to the lowest critical force. And when we solve for that, well, we can see here that when we insert n equal to 1 to find the lowest eigenvalue, then we here find the corresponding condition, and we can then insert that into the definition of lambda, which was defined in terms of the force, and we can derive the critical force, which corresponds to the second case in the table that we looked at previously. So this is where the factor of pi, this little bit funny factor of pi squared comes from, is from solving the eigenvalue problem here that involved a sine function. As it's important to understand that we have several values of the critical force. We will also have values for n increasing, but they will not really be relevant, of course, because if we increase the force from 0, at one point we reach the first critical value, and then we have buckling. And then all other values for higher values of the force will, of course, not be relevant at all. So it's always, or most often, it's the lowest buckling mode that will be important. This is not generally true, but for these simple problems, we will only be focused on the lowest critical value of the force. These calculations were done for the specific case of a simply supported beam, that is, with simple supports in both ends. Now, if we have other boundary conditions, we need to take a more general approach. As described in the textbook, we have a calculation based on moment equilibrium. I will give a slightly alternative derivation of these equations and how we get to our generic equation that is shown here, which is a fourth order differential equation. So I will just spend a bit of time on doing an alternative derivation. Now, in this case, we have drawn here a force diagram for the beam in the case of a general shape, general boundary conditions. So we have taken a section, the last section of the beam. So our point X here, we have an arbitrary point in our beam. We have made a cut, and we have indicated our cross-sectional quantities, moment, shear force, normal force. And then we have the end of the beam, that is for x equal to L, indicated over on the other side. And here we have just indicated a force, a moment, and a vertical force, a reaction force, that could represent any type of boundary condition. So we do not know the boundary condition here. They could be anything. So we take this as a starting point, and then to compute the quantities that we need, we take a moment equilibrium around x. Now, when we do this, let me just erase this. Okay, when we take the moment equilibrium around x, of course, we need the moment in our cut, mx appears, and this we are taking the moment of the section to the right of our cut. So our mx will point in the negative direction. Of course, also we have mb giving a moment at our boundary. So this acts in the positive direction. Now, depending on the deflected shape here, or the buckled shape, we will also have contributions of our force F and our force RB onto our moment. So in order to quantify the moment contribution, we simply have to indicate the deflection here. So this is W at the point X, but also we have here, corresponding to this point, we have W at the point L here. So this will match our position of our endpoint here. Okay. So if there's a difference between WL and WX, then our force F will give a moment around point X, right? That corresponds to the different height positions of the action point of our force and our cut. So we will have minus F, and then the difference, WL minus WX, or let's just call it W here. We can call it WX. Okay, so this is our deflected shape. And then, of course, our RB will also give a moment contribution. So this is a moment contribution, assuming some arbitrary buckle shape. We can use that to express our moment x. So we just reorder our equation here. MB plus RB L minus X minus F WL minus WX, like this. Now, just as we did for the more simple case of a simply supported beam, we have the definition of the moment that we can use. So the definition of the moment is that the moment is equal to minus the bending stiffness, EI, multiplied by the second derivative of our deflection shape, so our W or our WX, right? And that means that we can insert that. We insert that into this position. So we just reorder with the minus sign, and then we get EI W prime prime equal to minus B, MB, minus RB, L minus X, plus F, W, and now we just omit the X quantity because this is the position-dependent deflection, so we don't really need to write the X subscript. But this is the deflection at the end, right? WL. Okay, so now we go ahead with the differentiation. We can always do that. So we differentiate twice. And now we just put the parenthesis because in principle our EI could be non-constant throughout the beam length. So we differentiate outside the parenthesis. So our MB is simply a constant. It's the moment at the end. We don't know what it is. It could be non-zero. But anyway, when we differentiate, it vanishes. We have a contribution from the second part, our second parenthesis, where we get RB only. Differentiating the quantity RB times X gives us RB. And also the last parenthesis, we get F is a constant. So we get let's see here. I find out there's a small sign mistake. This should be L. This should be, whoops, like this. So when we differentiate this part, we get minus F times W prime. And then we differentiate once more. Now we differentiate RB. This is, of course, 0 when we differentiate. And now we then differentiate the second term. And we get this quantity. And we can put that on one side of the equation sign. We get EI W prime prime and then prime prime again plus F times W prime prime equal to 0. And then for constant bending stiffness, well, we get EI W and then 4 times prime plus F W prime prime equal to 0, or expressed in the same way as we expressed the second order differential equation. Now we express the fourth order differential equation using a parameter lambda squared like this. And our parameter lambda squared in this case becomes equal to F divided by EI, like this. So this is the general formula that we need to solve with the specific boundary conditions. And of course, this is a fourth order differential equation. It's a little bit more difficult to solve compared to the second order differential equation. But let's take a look for an example. So our example will be the fixed simple beam that we have shown here to the right. So we have a fixed, clamped, we should say clamped instead. Let me just erase that. Clamped. So clamp symbol, clamped at left end, simple supported at the right end, and we have an actual force F. So our boundary conditions are stated here below the beam. Our deflection and our slope at x equal to 0 would be 0 at the clamp part, and our deflection and our moment corresponding to W prime prime are 0 at the right end, corresponding to x equal to L. So now we're solving the fourth order differential equation, and we are interested in the lowest critical force that will give a non-trivial solution of this equation. Now, as I said, the fourth order differential equation is a little bit more difficult, but this is still a standard differential equation where we can look up the solution. So the solution to this equation is a sum of 4 contributions. So we will have a cosine lambda x, we will have a sine, but then we will have 2 additional terms. We will have a linear term, and we will have a constant here. So this is the general solution to this fourth order differential equation, at least one way of writing it up. Now, when we employ the boundary conditions, we need both expressions for the slope and also the second order derivative. So let's write that up. So W prime get when differentiating the last parts like this. and then also the second order derivative. Like this. Now we have all we need in order to employ our boundary conditions to determine our 4 boundary conditions A, B, C, and D. Now let's take the easy ones first. Usually it's most easy to employ the boundary conditions for x equal to 0 first. So let's do that. W of x equal to 0. Inserting that gives us that A plus D must vanish. So far so good. W prime of x equal to 0 is also equal to 0. Now inserting that, we get that B lambda plus C lambda equal to 0. Meaning, of course, also that B plus C equal to 0. Yes. And now going forward, we can see here that our next thing that we could use, we still cannot explicitly determine any of the constants. We still need to go a little bit forward. As the next choice, we'll look at W prime prime of L equal to 0. Now inserting that, we get minus A lambda squared cosine lambda L minus B lambda squared sine of lambda L equal to 0, which in turn, after shorting out the lambda squared term, we get minus A cosine lambda L equal to B sine of lambda L, or written differently, tangent of lambda L being sine over cosine equals to minus A over B. Now still a little bit of work to do, so we take the last condition, W of L equal to 0. Inserting A cosine lambda L plus B sine lambda L plus C lambda L plus D equal to 0. Now we can use some of the conditions that we have written up. So we know that, for instance, D from this condition equals to minus A. We can use this to express C as minus B. Insert that, we get A cosine lambda L plus B sine lambda L minus B lambda L minus A equal to 0. Now we can collect the terms. So terms of A, we get cosine lambda L, and we get minus 1 A. And then we're collecting terms of B, sine lambda L minus lambda L, B equal to 0. Now we can also express our coefficient A in terms of B from this equation. So we can here express that our A is equal to minus B tangent lambda L. Now we can insert that into this expression here. So we have cosine lambda L minus 1, and then we get tangent lambda L B, and we have the minus, don't forget that, plus sine lambda L minus lambda L B equal to 0. Yes. Now we can see here, now we have expressed everything in terms of a single constant. And again, of course, we are left with the fact that B equals to 0 is also a solution. Now, if B is equal to 0, A is equal to 0, D is equal to 0, C is equal to 0, then we just have the straight beam. That's the trivial solution. But if we shorten out B from the last equation, we can find the condition for lambda L that leads to the non-trivial equation. And now we're close to the end, because after shortening out B from this equation, simply canceling it out, assuming that it's non-zero, then we get the following equation, and we can just multiply that out a little bit. Now, multiplying cosine with tangent gives us a sine. So we have minus sine lambda L plus tangent lambda L plus sine lambda L minus lambda L equal to 0. Becomes more easy here because we see that these terms cancel out, and we simply get tangent lambda L equal to lambda L. Well, this is of course a nonlinear equation in lambda L. We can solve it, and we get that our lambda L equals to 4 times 49. Meaning then that inserting the definition for lambda, we get that our critical force in this case becomes 4 times 49 squared EI L squared, which matches exactly the formula that we showed for the third case of our of our table in the beginning. So we see here now we have to solve, in order to get this, we have to solve our fourth order differential equation, taking 4 terms, employing the boundary conditions at both ends, and then we arrive at the answer. It's not simple calculations, but it has been done for many boundary conditions, so we can simply, in most cases, look up the example or look up the result in a table. Now here we see a summary of the solution that we just outlined in more detail, and we see also in figure 7.4b the graphical illustration of the solution leading to the factor of 4.49, that is the characteristic quantity here for the eigenvalue. And we also see in figure C the characteristic buckled mode shape. And remember always that the solution gives only the shape and not the magnitude of the buckle load of the shape. Now we will finalize our treatment here of the buckling with another example, and it's taken from page 299 in the book, example 7.1, and it shows how we apply different boundary conditions than are given in the standard elementary cases, the 4 cases here. Now we have the simply supported beam, but as an added complexity here, we have added a moment spring at the right boundary. So now we want to see how does that, of course, how do we treat a problem like this, applying a non-standard boundary condition, and how does it affect actually the solution for the critical load. So what we want to find, that we state up here, we want to find the critical load for the system, and we want to find it in the specific case where the torsional spring stiffness, our KT, has a specific value that makes the product of KT times the length divided by the bending stiffness equal to 10. So it's just an arbitrary value, but for this specific magnitude of the torsional spring constant, we want to find the critical load. So now all the standard things are written up here. So the solution with the 4 characteristic terms, the cosine, the sine, and the constant, the linear and the constant parts, with our 4 unknown constants A, B, C, and D, are written up. Also the first order and the second order derivative that we need to employ the boundary conditions for our specific problem. I've also written up the trivial boundary conditions. What do we have? Well, at the left end, it's simply a simple support. We have the deflection equal to 0. We have the moment, hence the second order derivative equal to 0. At the right end, we have, of course, the deflection equal to 0. It's a support. But the second boundary condition, of course, has to reflect the fact that we have a torsional spring. So we don't have a 0 moment as we do with the normal simple boundary condition. So how do we write it up? Well, let's just take a look at what happens here. So we have our beam end here, and we have the moment spring. So we have a slope at the beam at the point of the support, and the slope gives rise to a moment, right? So we have a moment coming from the support. So remember, the moment in a torsional spring is given by the torsional spring constant times the angle or the slope. So it's actually the slope at x equal to L, right? So we call W prime of L. And we also know that the moment is equal to minus EI times the second order derivative. So that means that our moment here will then be expressed as the value of the specific moment due to the slope and the moment spring here. Now, so this constitutes our second boundary condition, which is specifically derived in terms of a moment spring at the right end. Now we can then use these boundary conditions. So let's first take the trivial ones. Inserting W of 0 equal to 0 leads to the condition that A plus D equal to 0. Now W prime of 0 equal to 0. Now that condition gives rise to the fact that minus A lambda squared, lambda squared equal to 0. So A is equal to 0. Well, that also, of course, means that D is equal to 0 according to the formula just above. So two of our constants will be 0. So this makes life a lot easier here. Now let's employ the third trivial boundary condition. Which gives a condition or a connection between C and D and B. So inserting, get sine lambda L divided by lambda L B. And now, of course, we're ready to employ our non-trivial boundary condition. So employing that, we get minus. Okay, let's just write it up. Minus EI W prime of L equals to KT W prime of L. And inserting, we get EI B lambda squared sine lambda L equals to KT. And then we get B lambda cosine lambda L plus C lambda. And we can, of course, instead of C, we can use the connection that we found here. The L, and I'll just move B to the end here, and we can do the same over here. We can insert KT, of course. We have B cosine lambda L, and now we insert the specific value of C, which we found from the connection above. So now we can see that we have arrived at the equation where we only have the factor B as the unknown coefficient. Again, B equals to 0, a solution. That's not the one we're interested in. We're interested in the solution where B is not equal to 0. We cancel out B from the equation. We arrive, now let me see here. Yeah, then we arrive at the top equation. And this simply we have to solve for the case of our unknown eigenvalue. So I already did one simple calculation here, and we can further simplify stuff. So we have sine lambda L and cosine lambda L. We can convert that to a tangent. So doing that, we find the equation tangent lambda L, and then we can rearrange the terms, and we get this kt times L divided by the bending stiffness, multiply by a factor lambda L, divided lambda L squared, and then again the factor. And the reason, of course, why we have created this factor of kt times L divided by the bending stiffness is that in the exercise it was given that exactly that this factor was equal to 10 in our specific case. So this means that we can write up as 10 times lambda L squared plus 10. Now this equation, of course, again, complicated equation in the factor lambda L, a nonlinear function, and we need to solve that using some kind of software or a pocket calculator. So doing that, we get, inserting then again the value of lambda, we get that our F critical in this case equals to 17.1 becomes the interesting factor here, and then EI divided by L squared, right? Now, one thing that's a little bit interesting here, a little bit cool, is that we can actually use this equation that we have here for two specific limit cases. Now, a moment spring, if we have the case that kt equal to 0, meaning we don't have a moment spring, then the result actually, of course, converges to the simple result. And on the other hand, if kt goes to infinity, then the results converge to the case of a simple clamp beam. And then for any intermediate value of our kt, and here specifically for ktl divided by EI equal to 10, we get an intermediate result with the F critical attaining the value given by this value here. Now this concludes the theory for today. So yes, so we are ready now to do the exercises, and it's a little bit of mixture, of course, of the buckling, but also a little bit of repetition of the composite beams. So we have two exercises, B26 and B30, and then we have an extra exercise, X13. So have fun.